Right, let's have a look at acids and bases on paper 3, specimen 0.5, paper 3. So I've got a graph showing it looks as if some sodium hydroxide, it's got very high pH, going up to pH 13, has been added to something pH 2. Maybe it's a weaker acid, ethanoic acid, yeah, weaker acid. Got a high pH for a weak acid at the beginning, but it says it's ethanoic acid, so it's a weak acid and a strong base, sodium hydroxide. The pH is going up rapidly in between around about pH 7 and 10, something like that. So the equivalence point is halfway between 7 and 10. So, but it's going up rapidly between 7 and 10, so I'm looking at something that fits in between 7 and 10, higher than 7 but less than 10, so the answer is thymol blue. 89.6 is within 7 to 10. And for that curve, by the way, as before I've done previously, you'll be adding sodium hydroxide using burette, which delivers different volumes, small amounts at a time, to your ethanoic acid, stirring and measuring the pH as you go with the pH meter. The uncertainty in the mean titration is 0.015, so you take the percentage uncertainty and you divide by the volume. Where does it tell you the volume? The volume that you delivered. I don't know where it tells you the volume. Calculate the percentage uncertainty in this mean titration. It must tell you earlier in the question, I think, that the volume is 3.98, so that's your average volume between the two readings. So I'm not multiplying by 2 because it says I've already calculated the mean between the two, so I just do the percentage uncertainty 0.15 divided by the reading. Would normally multiply by the number of readings, 2 for a burette. It says that that's already worked out because you've done the mean titration already. 3.98 encompasses both readings. Multiply by 100%, 3.77. Suggests how using the same mass of ethanoic acid the experiment could be improved to reduce the percentage uncertainty. Well, you want that reading to be bigger. So as that reading 3.98 is bigger because it's on the bottom of the fraction, if that's a bigger number then your percentage uncertainty ends up lower. So you need a bigger volume of sodium hydroxide. How do you get a bigger volume of sodium hydroxide? You lower the concentration of sodium hydroxide, so a larger volume is required in the titration. Multiple choice, pH 0.02, solution of a diprotic acid. Diprotic acid is something like sulfuric acid, where 1 mole of the acid makes 2 moles of H+. So if I've got a concentration of 0.02 moles of the acid, I get twice the amount of H+ released when the diprotic acid dissociates. So 0.04 is my moles of, my concentration of H+, minus log to the base 10 of it, 1.4 seems reasonable for an acid. The acid dissociation constant Ka of a weak acid has the value 2.56 times 10 to the minus 4. So if I have a weak acid, something like HA, as it says in the question, it's going to dissociate to make H plus and A minus. Write an expression for the equilibrium constant, the acid dissociation constant, H plus multiplied by A minus divided by HA. As a molecule of HA dissociates, breaks, splits, it'll split into H plus and A minus, so I can turn that into H plus squared. 0.000256 equals H plus squared, divided by the concentration of HA, which is 4.25 times 10 to the minus 3. Work out H squared, square root it, and you'll end up with 0.01. If you do pH of that, it'll end up as pH 3. So your answer is C. That's the one closest to pH 3.